My name is Toni Sauncy, and I am the chair of the physics department here at TLU. And we're really honored to join you today for this lecture in honor of Deborah Hedinger. She was a legend here at TLU, and as a woman in science, I'm especially honored to be carrying on this tradition.
I'm Calvin Berggren, one of the physicists here in the department. My research specialty is in particle physics. I'm doing mainly like theoretical and computational work.
And I'm Josh Fuchs. I'm the newest faculty member in the department. I'm an astronomer by training, and I'm particularly interested in dead stars that we call white dwarf stars.
So I sit between a person who studies the very most tiny parts of the universe and someone who studies the biggest parts of the universe, and I study the sort of more boring stuff that we use here on this planet, electronic materials. So we're going to start today by thinking about some of the big questions that physicists are asking around the world, not just here, but everywhere, and thinking about how we go about answering those questions. So we'll start off with Dr. Fuchs.
So one of the first questions you might think if you're asking questions about the universe is exactly how big is the universe? So we're going to start off with a little video here that's going to give us a sense of exactly how big the universe is. So in this video, we're going to be zooming out and looking at things as they get larger and larger. So for example, you can see an elephant here. As we zoom out, we can see Boeing 747s, redwood trees, the Statue of Liberty. As we get to larger and larger things, you can see the Titanic and the Gateway Arch. There's Half Dome out in California. As we keep moving out, we see there's Central Park. Now you can see the Large Hadron Collider. We'll talk about that later. There's Rhode Island. We're getting out and seeing larger and larger structures. You can see West Virginia, and California is coming in here on the right. So you can see Italy. Now we're starting to see some planets and some moons around other planets. There's the Earth here on the left. As we move out, you can see star Sirius B. There's Neptune and Uranus and Saturn and other planets. Now we're starting to see some stars. I think this is going to be our sun here on the left. Now we're seeing stars that are bigger than that. You can have stars that are up to about 100 times the size of the sun. So as we keep moving out, you see other stars that we know about in our galaxy that are larger and larger. We keep moving out and we see some of the largest stars that we know about in the universe here. Now, we've reached the biggest size that stars can form, and so we start to see large structures of hydrogen gas called nebulae. This is where stars are formed and where stars die. There's a whole bunch of different ones that we'll see there. There's the Stingray Nebula. The bottom here, that's the Cat's Eye Nebula. And so these are many, many light years across. And there's the Eskimo Nebula, the Ant Nebula. So we're zooming out. We're seeing some of the largest structures that we know about in our galaxy alone, that are multiple light years across. And in a second here, we're going to start to see collections of stars. So if you have just a few stars, that's called just a cluster of stars. But if you have billions and billions of stars, you start to form what are called galaxies. So, for example, the Large Magellanic Cloud is a very small galaxy, but now we're starting to see other galaxies. There's the Milky Way, which is where we live, Pinwheel Galaxy, the Whirlpool Galaxy. So now we're seeing collections of galaxies. So these are called clusters, galaxy clusters, formed up of multiple clusters. And as we continue to zoom out, we're starting to see some of the largest things that we know about in the universe. And so as this video zooms out, these are some of the largest things that we know about, the largest structures that we can know in the universe. And so what we're going to see here is the farthest back that we can see. This is the observable universe here. So that's really the size of the universe that we can see, and we'll talk in a moment about how exactly we know that.
So physics asks really the biggest question in the universe, how big is the universe? But that kind of leads us to a very important question, I think, and that is, how do we know all this? That was a video that was constructed by cartoons and such. So how do we really know how big the universe is?
Well, it turns out it just comes down to light. So light has many different forms, and you can see on this graphic here, these are the different forms of light that we know. So we start on the left. we have the highest energy types of light. These are what we call gamma rays or X-rays. And as we go to the right, we're having light that just has not as much energy. So some of the lowest energy light that we have are microwaves or radio waves or very long radio waves. In particular, you can see the visible spectrum here, right? This is what we can see with our own eyes. This is the rainbow that we can see. And so we only see a very small portion of the different energies that light can have. And so by astronomers, right, we can put together telescopes and arrays that look at different types of light, and from that we can study different things that are happening in the universe and put together this picture that we have. So in particular, one of the ways that this was done, one of the major discoveries in astronomy that helps us to know exactly how big the universe is, was done in the mid-1960s by two scientists at Bell Labs, Penzias and Wilson. They were using a radio telescope, so they were looking around the galaxy at sources emitting radio waves in the galaxy. And they found that there's a source of noise that they couldn't get rid of. It just happened to be there all the time. And so they tried to get rid of it in multiple ways. They scooped poop droppings out of it from pigeons, I believe. But they just couldn't get rid of all of this extra noise. And so what they eventually figured out was that this is actually a real source of light that's coming from the universe, and it's what we call the cosmic microwave background. So this cosmic microwave background has been mapped multiple times since then, and so let's take a look at a video that shows exactly how hard it is to measure this, and then we'll talk about why it's important that we can measure this. So this is a video from the Planck mission done by the European Space Agency. And it's going to show you, so the mission operated for about 15 months, and this is what the image looked like at the end of this 15 months. It's looking at the universe in radio waves. And so highlighted here are all the individual sources. So these are stars and galaxies. And so if we subtract all of those individual radio sources from the picture, this is what we're left with. Then our galaxy itself, the clouds of hydrogen gas are also emitting light. So if we subtract those, we're left with this. There's tons of dust in the Milky Way galaxy as well that emits radio waves. And so if we subtract that, we subtract all these different sources, and we're left with this image here, which is called the cosmic microwave background. So this is the earliest light that we can see in the universe. For the first about 380,000 years that the universe was around, the universe was too hot and too dense for light to actually travel very far. But eventually it cooled off enough and light could start to travel for longer and longer distances. And so that time occurred when light could start traveling for long distances, about 380,000 years after the Big Bang. And so as the universe has continued to expand and cool off, we can see back to 380,000 years after the Big Bang. And it turns out that this temperature that we can see now is just above absolute zero at about 2.7 degrees Kelvin. So if you look at this plot as we've shown here, this diagram of this cosmic microwave background, you can see all of these different speckles. And so this is just plotting different temperatures at different places on this background. But the key to note here is that that there's not much temperature variation. And so the temperature variations from hot to cold here are somewhere around 0.0009 degrees Fahrenheit. So that's very, very small, practically very difficult to measure and practically unnoticeable. But these very small temperature variations give us clues about how the early universe developed, how the early galaxies developed, and how they started to evolve over time.
So through the discovery of cosmic microwave background radiation, we've really learned a lot about the history of the universe, how it developed, how big it is. But there's one thing that we know for sure, and that is that the universe is anything but constant.
But that's actually the question that astronomers were asking themselves in the 1920s. So there were two astronomers who really helped solve this mystery. On the left, you have the Belgian priest and cosmologist Father George Lemaitre. And then the right is American astronomer Edwin Hubble. So these two guys were approaching this question from different ways. Lemaitre was working out the calculations of what happens to the universe and is it changing over time. And Edwin Hubble was using the 100-inch Mount Wilson telescope out in California, shown here on the left, to look at galaxies. And so as he looked at galaxies, what he realized is that no matter which direction you look as you look at galaxies that are further and further away, they're each moving away from us. And so this taught Hubble and taught Lemaitre and taught the rest of the astronomical community that the universe is actually expanding over time. So let's take a look at what this actually looks like.
So we can demonstrate this idea of everything moving away from everything else with a simple balloon. If you notice on the balloon, I have dots. So I want you to pay attention to what happens to the space between the dots as I blow up the balloon.
So you're noticing here the dots are getting farther apart as the balloon expands. The dots were drawn onto the balloon with just a marker, and as the fabric of the balloon stretches apart, we see the dots stretching farther and farther apart. This is kind of an idea that we have about how the universe expands, which is that each dot would represent a galaxy, and that as the space itself is expanding, just like the fabric of this balloon, then the galaxies are receding apart. And this is our understanding of why the galaxies recede apart from each other. I think one kind of cool point to notice about this is that Einstein taught us that space is actually a curved object, just like the surface of the balloon is a curved object. But as it gets larger and larger and larger, it starts to appear more flat between the different points. So what we observe in our universe now is that the universe is very flat. We notice almost no curvature at all. And the idea is that it's expanded to the degree that we just don't see it anymore.
Investigations by Hubble and other scientists have led us to a very insightful understanding about the universe, about how it started, how it behaves now. But maybe the next question we should be asking is, what is the universe made from?
And the universe, what's made from, is a very interesting subject. We can look at this on a number of different levels, which I think is very interesting. So to start off with, we have a slide here that shows the standard model of particle physics. This would be what we call matter. So everything that we know of, everything that you see outside, what's in front of you, your body, everything is made of matter and is made of a number of subatomic particles, which are shown in the chart here. You see a variety of different particles. These are the most fundamental particles that we as physicists know about at this time. You see things like quarks there. You see things like electrons, things like neutrinos. Electrons, one of the most familiar particles that we study. All of us study electrons in a variety of different ways. But there's many other particles that are very important, very interesting, and all kind of go to describe matter as we know it, atoms, and even smaller subatomic particles and the interactions that are between them. But it turns out, very interestingly, that matter actually is a very small piece of what we know of. So if you look at the pie chart on our diagram here, you'll see that atoms actually make up just about 5% of the known universe. You'll notice the next largest section of the pie is actually what we call dark matter. This is kind of an interesting substance because we really don't know exactly what it is. This is just something that we see a variety of evidence for in a variety of observations that we make astronomically, cosmologically, and a variety of different ways. So dark matter, we kind of see indirect evidence of it, but it's really an open question as far as what it actually is. There's a lot of things that we've been able to infer kind of about it, things about how galaxies rotate around and things like that. We have a slide here showing our best understanding of what the dark matter halo looks like. So the dark matter halo is essentially, this is a graphical representation of what we think the dark matter distribution might look like around our galaxy. You'll notice that the halo is actually significantly larger than the galaxy itself. It has a roughly spherical shape, and as far as we know, this halo formed at the same time as the galaxy and provided the kind of gravitational perturbations that were needed to allow the galaxy to coalesce, clump together, and start to form the clumps of matter that we call stars today. And so this is really an instrumental part of how galaxies are formed. This brings up a lot of interesting questions because we don't actually see these particles of dark matter directly. We just kind of infer their existence in a number of different ways. So scientists are studying a lot of stuff about, what is dark matter actually? What is it really made of? What's kind of its identity? And there's a lot of new physics on the horizon that we feel like is up and coming. One of the things that the ways that we study it is through what we call direct detection experiments. And we have a picture of one of those. These are these gigantic vats of, liquids like xenon that are just made to detect collisions with these dark matter particles that may be happening very, very small amounts. It seems to be that there should be dark matter kind of permeating the entire galaxy. Even in the room where you're sitting right now, there are dark matter particles moving around. But the thing is that they really don't interact, except very, very, very rarely, with anything else. These very sensitive experiments like Xenon 1 ton that we have a picture of here are designed to be these extremely large experiments and extremely sensitive to try to detect these very rare collisions with a dark matter particle and try to pick up evidence of those. So there's a variety of experiments like this that are really trying to get at that really fundamental question. The question is actually not quite as strange as it might sound. There is another kind of a particle called the neutrino that we actually feel like we understand fairly well today, but has a lot of similar properties. Things like that it really very, very rarely interacts with anything. So there actually are a very large number of neutrinos passing through your body right now that you don't even realize because they interact so rarely with anything that we know of. But yet we've been able to be successful in designing large experiments that have been able to detect the presence of neutrinos because we have a sensitivity which is low enough that we've actually been able to get to that level. The hope would be that dark matter follows a similar kind of a pattern, that hopefully we will be able to gain sensitivity by building bigger and more sophisticated experiments. People actually thought at one point that neutrinos might be dark matter if they had a mass that was enough to provide evidence for it, but it was discovered at some point that the matter is just not high enough in mass to account for it. So kind of the search is on to find more and more exotic particles that might provide an explanation of that. Another way that we try to study dark matter would be through a particle collider. So this kind of gets a little bit closer to my field. We have a slide and a picture for what a collision looks like inside of a detector, and how there's a variety of different particles interacting, colliding, decaying, and kind of passing through different detectors of different sorts. By looking at all these particles and detecting what they are, where they came from, it's possible for us to reconstruct what the original interactions were, even see evidence of particles that may have been there and may have escaped the detector, things like neutrinos or possibly even a dark matter kind of a particle. But in summary, dark matter is a very exciting field because we really don't know what it is. There's a lot of very interesting clues that we've found so far, and there's a lot of really exciting and interesting physics kind of on the horizon as we continue to investigate and try to find out more about it. If we return to the pie chart, you'll notice that the dark matter actually is not even the largest part of the pie. There's even another component which we call dark energy, which is possibly even more mysterious than dark matter. We possibly have even less information about what that is. But again, we kind of infer the existence of another form of energy that's kind of propelling the universe to expand outward at an ever greater rate. So we have very good idea that there is something out there, but we don't have a really great idea about what it might actually be as far as its identity. The best idea so far would be that there's actually a connection between dark matter and the vacuum of empty space. People theorize that the vacuum of empty space actually makes a noticeable contribution to the energy in the universe, and even to the point that it is the dominant factor of energy. It turns out that, maybe surprising, but the entire universe, by and large, is just empty space. It's just a vacuum. There's literally nothing out there. No particles, no atoms, no air, no dust in space. It's really like an extremely, extremely just large amount of nothingness, which we feel like may have a connection to the dark energy. So a lot of exciting questions about what physics is made out of. And I'm excited to be able to study that from the particle physics perspective.
So we've covered some extraordinarily big questions about the universe, and most of them really do not have very satisfying answers, which is a driving force behind why scientists remain curious about the universe and everything in it. So I guess the next question is, where do we ponder from here?
Well, so it turns out that to ask these big questions and to answer the big science questions that we're asking today, we need really big science facilities. This is the James Webb Space Telescope, or at least an artist's illustration of what it's going to look like. James Webb is the successor to Hubble. It's going to be launched by NASA in October of 2018. It's currently at a facility in Houston undergoing tests. James Webb is much bigger than Hubble. The primary mirror of James Webb is about 6 meters, which is close to about 30 feet across. The whole spacecraft is about the size of a tennis court. And James Webb is going to be big enough and sensitive enough to be able to look back into the early moments of time as far back as we can, close to this cosmic microwave background, to answer questions about how the earliest galaxies formed, how they evolved over time. It's also going to be able to look closer to us at planets around other stars and help us understand how those planets form and evolve over time. As a complement to that, there's a range of extremely large telescopes coming online in the 2020s. Here we're showing what's called the Giant Magellan Telescope. These telescopes are going to have mirrors that are collectively somewhere around 80 feet across. So they're many stories tall, many stories wide. These are gigantic buildings that they're going to be housed in. And these telescopes are also going to be looking at planets and some of the earliest galaxies and to understand and ask these big questions. Finally, also, Calvin just mentioned the Large Hadron Collider, which is shown here. And so that's just really started going a few years ago. And so there's lots of exciting science from that we're all looking forward to seeing in these next few years. And so we thought we'd end with something that has happened in the past couple of years, in which you might have heard about, and which you're going to hear about more in the next couple of years as well. And this is the Laser Interferometer Gravitational Wave Observatory, or LIGO. So there's 2 of these in the US, these 2 gigantic arms, each is about 2.5 miles long. And light is shot down each of these arms back and forth. And by very, very subtle changes in the length of these arms, if these gravitational waves pass through these arms, we can detect those. And so this is something that Einstein predicted about 100 years ago. And these measurements are difficult enough to make that it hasn't been until the past couple of years that we've been able to find them. So to date, LIGO has detected 3 gravitational wave events. This shows a simulation of what's happening. So you have these 2 gigantic black holes that are somewhere around, one is about 10 times the mass of the sun, one's about 30 times the mass of the sun. They're orbiting around each other. When they get too close to each other, they actually collide, and as they're going through that, they send out ripples in space-time, and it's these ripples that this LIGO observatory can actually detect. And so this is an entirely new way to look at the universe, to study these gravitational waves. And so as we detect more black holes colliding and possibly neutron stars colliding with black holes, it's going to help us understand some more of the physics about how exactly the universe works and questions that we can ask about it. So this is a simulation of what this actually looks like. We have our 2 black holes here in the middle. You can see they're going around each other, and you can see the blue and the yellow are our gravitational waves that are spreading out. So as these 2 black holes get closer and closer, they go around faster and faster, till eventually they collide, send out a big ripple, and we're left with just a single black hole in the end. So as these 2 black holes were colliding, they sent ripples throughout space-time, and it's these detectors here on Earth here, and there's one in Louisiana and one in Washington that just detected in the past couple of years these gravitational waves.
So we've posed a lot of big questions about the universe. We hope we've given you some answers, but I hope more than anything, we've given you pause to ask even more big questions about how things work.